So by Bohr invoking the idea of classical correspondence as or the classical limit being an extension of the quantum mechanical formula, he was able to derive an expression for the Bohr radius in terms of fundamental constants. And I will invite you to insert the value for Hc, which is 1240 eV angstroms, or eV nanometers, in the electron mass, and the value of the Coulomb charge. You will, in fact, find that you get an exact prediction for the Bohr radius. Remember that the Bohr radius was also related to the Rydberg constant as follows. And this gave us a prediction for the Rydberg constant which exactly agreed with the experiment. Namely, the value that was required to fit the Balmer data. So the amazing thing about Bohr's theory at this stage is that it does predict these empirical numbers in terms of fundamental constants, and it also gets the energy levels of the atom approximately correct. There are some assumptions that we have to keep in mind. First of all, the nucleus is infinitely heavy. If that was not the case, then this quantity here in the denominator would not be the electron mass, but rather reduced mass. So if the nuclear mass is capital M and the electron mass is little m, the reduced mass approaches the electron mass as the nuclear mass gets to be infinitely large. That's the quantity that should, properly speaking, go in there. If the nucleus has a charge that's larger than just one electron charge, in other words, we're not talking about hydrogen, but rather some other larger nucleus with charge plus CE, then in the various places where we've expressed the Bohr radius as E squared, as being related to E squared, that's to be remembered as the electron charge as the proton charge. So here would be a factor of Z, or in the case of the Rydberg constant, there would be a factor of Z as well. The other assumption here is that there's only one orbiting electron. If there are in fact multiple electrons orbiting the nucleus, then in fact each of them exerts a Coulomb field on each other, and that can complicate the picture that we've painted here. So the Bohr model as it stands is really only best at doing predictions for nuclei with a single electron orbiting around. That might be, for example, predicting the levels for helium plus or beryllium that's been triply ionized, or lithium that's been doubly ionized. In these atoms, or these ions, only one electron is orbiting.